Let's talk about relative motion with a really simple example. So I have a surface, and I have two masses on this surface. We'll call mass A, mass B, and they're moving toward each other at constant velocity. And so if I want to if we sort of describe this, we have a coordinate system here that will say this is the positive x direction. Here's a positive y. And so given that, we can say that, let's say mass B has a velocity then of -2 meters per second, I hat, is negative x direction, and the velocity of A would say positive 2 meters per second, I hat. And so given, and that these numbers then, these values of the velocity are given relative to a particular coordinate system. And this coordinate system here is fixed relative to the surface that the masses are moving on. Okay, and so what we want to say, what we want to consider is imagine then that this surface that these masses are on is in fact some sort of railroad car that itself is moving on the ground. And we'll say that this car is moving forward at a speed of 2 meters per second. Well, 2 meters per second along the ground. And so what we want to do now is we want to set up a second coordinate system. And so in this, we say this is a positive x and a positive y. And so now we have two coordinate systems themselves that are moving relative to each other. And really what we have is we have two objects. We have sort of this train car and the ground, and these two objects are moving relative to each other. So we establish coordinate systems on each, and we describe then the motion of the coordinate systems relative to each other. And so now we want to ask the question, how are the masses moving relative to the ground when we know how they're moving relative to the railroad car? Okay, and so the first thing that we establish here then is the velocity of the two coordinate systems. And so we say the velocity of the car relative to the ground then is this 2 meters per second I hat, right? And so we know that the velocity, let's do mass A, the velocity of A relative to the car is equal to 2 meters per second I hat. And so then it becomes to find how it's relative to the ground, the velocity of mass A relative to the ground is simply the velocity of A relative to the car plus the velocity of the car relative to the ground. And so I've sort of used the words to describe this relationship, and sort of this notation that goes along with it is sort of there to help remember how this goes. So here's the mass of the object, and I want to know it relative to the ground. And if I think about this subscript notation, here's the mass relative to the car relative to the ground. If you think about these subscripts, you multiplying them together, you sort of cancel the c's and you get A divided by G equal to A divided by G. That's not what's really going on, of course, but it's sort of a little device to help remember how these pieces fit together. If I want A relative to the ground, and I know A relative to some other coordinate system, in this case the car, then I can use this relationship where A relative to the ground is equal to a relative to the car plus the relative velocities of the coordinate system, car relative to the ground. Okay, and so let's use this in this simple example. In this case, the velocity of A relative to the ground is equal to 2 meters per second I hat, plus then the velocity of the car relative to the ground is 2 meters per second I hat, and then 4 meters per second I hat. If we were to do the same for velocity of mass B relative to the ground, well, that's equal to the velocity of mass B relative to the car, which is negative 2 meters per second I hat, plus the velocity of the car relative to the ground is 2 meters per second I hat, and so the result is 0 meters per second I hat. And so in relative to the ground, B is in fact at rest as the car is moving underneath it. And relative to the ground, A is going at 4 meters per second. So you can imagine if these two objects have equal mass, they have equal speed, when they hit each other, they might be at rest relative to the car, which means together they're going to be going at 2 meters per second relative to the ground. So that's relatively simple enough. Let's look at a couple examples. One of the very common way that you use relative velocities is when you have motion in a medium that itself is moving. So I have a little boat here that is traveling down a river. The boat can propel itself down the river with some velocity v, the boat relative to the river. But then the river itself is moving with a speed relative to the ground, and we want to know how the boat is moving relative to the ground. So let's consider the following problem. We have a boat, and it travels some unknown distance in some time, t1, and then it travels back, and we measure, and it goes back to where it started at some time t2. And given the differences in those time, can we determine what the flow rate is? So let's establish a coordinate system. Let's say this is the positive x direction, and this is all one dimension, so we can work simply in components. Let's give this as 0, and then the turning point is some value of x. Okay, and so we have our relative velocity. We want to know then the flow of the river. So we know that the velocity then of the boat relative to the ground is equal to the velocity of the boat relative to the river plus the velocity of the river relative to the ground. And let's see, this is what we want. Let's just call this velocity of the river. We know, we sort of use our ratio subscripts to know that we've set it up correctly, but for convenience, I'm going to call this the velocity of the river. This is the velocity that the boat can propel itself relative to the river, so we'll just call this the velocity of the boat. And then this we'll just call the velocity. This is relative to the ground. So with this expression, let's see if we can come up with the flow of the river. So what we know is that the boat took two journeys. So the first leg, and this is all constant velocity, the boat underwent some displacement. So that took place at some velocity v over some time, which we know is t1. The displacement then, which is the final minus the initial, given our coordinate system and how we've set it up, that's x minus 0, is equal to the velocity then, which was the velocity of the boat relative to the river, which we call vb, plus the velocity of the river relative to the ground, which we call v sub r, times t1. Okay, so now then for the second leg, now it undergoes a displacement, delta x and 2, which is equal to some velocity 2 times t2. So the displacement going backwards is the final position minus the initial, so that's 0 minus x. In this case, it started here and ended there. So it went at this v2, which then is if we call VB if we say VB is positive, it's the speed at which it can propel itself relative to the water. We can say that that is negative VB. It's going in the opposite direction, but the river velocity is still flowing in the positive x direction. So we'll sort of use this so we know that this VB is the same value as this VB times t2. That's equal to negative x. And so positive x then is equal to v of the river minus v of the boat relative to the river times t2. So we didn't really know x, we just know that the time necessary to go back and forth. And so we can use these two equations to eliminate x. And we have, from the first part, v sub b times t1 plus v sub r times the first time is equal to, over here, the velocity of the river relative to the ground, t2, minus the velocity of the boat relative to the river, t2. So I want to solve for the velocity of the river relative to the ground, so I'm going to combine these terms. We'll bring that over to the right side here. And so we have v sub r, which is the velocity of the river relative to the ground, is equal times t2 minus t1, and then bring this to the other side. And so that gives us the velocity of the boat relative to the river, t1 plus t2. Now solve, and I get the velocity of the river relative to the ground is equal to the velocity of the boat relative to the river times the ratio of t1 plus t2 over t2 minus t1. And so this is now a general expression for the speed relative to the river. Okay, I'd like to do, then that's a simple one-dimensional example. I'd like to do one more example with relative velocities, only this time in the vector form. So let's get our river back here, and my boat. And this time, I'm going to try to land my boat on the shore. And this is a distance of 10 meters away from where I am, straight down the river. And my river happens to be 16 meters wide. I'm going to say the velocity of the river relative to the ground, so the flow of the river is at 4 meters per second. And let's ask the question, what is the lowest speed I can give my boat such that it makes it to this position? And where is that velocity pointing? So this now is a sort of a vector problem. Now, the one thing I like about this is that, so we can write out, so here's the vector of the boat relative to the ground. This is what is going to get us to the ground, is equal to the vector of the boat relative to the water plus the vector of the water relative to the ground. And we know the vector of the water relative to the ground then is 4 meters per second. I hat, if we say here, let's get ourselves a coordinate system, plus x plus y. And you can play with components on this quite a bit, but in reality, this is a problem that's most easily solved graphically. So let's look at it graphically for a moment. So I want, at constant velocity, I want to make this displacement vector. So let's draw out the displacement vector. This is my delta x displacement vector. And that delta x displacement vector has a component of 10 meters in the x direction and a component of 8 meters in the positive y direction. And so at constant speed, then, my average velocity then is going to be this displacement vector delta x over some time, delta time. And I want to know what this is going to be that's going to give me a minimum time. So the first thing that I want to identify, which is interesting for this problem, is that my velocity vector is going to point in the same direction as my delta x. And so if I look at that, I have then over here in velocity space, here's my delta x, delta y. My velocity of boat relative to the ground then has to point along the same direction as delta x. And since I know from that these angles then are the same. So tangent of this angle theta is equal to 8 divided by 10. And so this angle theta is equal to 38.66 degrees. So now let's look at this expression here. So if this is the velocity of the boat relative to the ground, I know the velocity of the water relative to the ground. That points along the positive x-axis with a magnitude of 4 meters per second. And because of this relationship, I know graphically then that my velocity of the boat relative to the water, must make then a triangle from the velocity of the water relative to the ground plus the velocity of the boat relative to the water must equal the velocity of the boat relative to the ground. And so what I'm asked to do is what is the smallest value of the magnitude, smallest speed of the boat relative to the water that is going to get me to this point on the shore? And the answer to that is, well, it's the smallest length of vector that can still create a triangle between a vector along the x-axis and a vector pointing at an angle of 38.66 degrees from the x-axis. So to do that line, which is the shortest line, is the line that takes me directly to the green vector here that makes a right angle. So it is this red vector now is the smallest magnitude of velocity of boat relative to the water that will get me to the place that I want on shore. And now I have the triangle here, and I can solve for that directly. So I know that given this triangle, that the magnitude of the velocity of the boat relative to the water is equal to 4 sine theta. And then I can find the direction then by finding where this is pointing. So let's get another coordinate system set up here. I don't want that color. Ooh. So if I draw another axis here, there, I can look for, I want these components now on the x and y axis. So if this angle is theta, I then have this angle is also theta. And from that, I can find the components of this on the x and y axes. So the v sub x is equal to the magnitude v, and that magnitude, which I can calculate from here, was just 2.5 meters per second. So the x component is v sine theta, and vy is v cosine theta. And this, to calculate this out, was 2.05 magnitude. And then I look at the graph, and I see that's in the negative x direction, my figure. And vy is 1.43 meters per second. And so these are the components. So I like this example because it uses the vector description of the relative motion, but unlike many cases where the components are the easiest way to solve this problem is most easily solved graphically. So it highlights the importance to have many ways to solve vector problems and to be comfortable with them, so you can choose the method that solves the problem most easily.